Starting now.
Oh, you tell me in the last second. All right. Okay, well, welcome everybody. Well, thanks for being here in this pandemic times. And well, first of all, I hope that you are all healthy and your family and friends and loved ones are all staying healthy. And well, secondly, I think I congratulate Matthias, Carl, Matteo, and other organizers of the HoloTube for this great initiative, because that's really, this is something that keeps us connected and in the pandemic times. So I hope that it will stay after the corona also, and I hope that there are some plans for that, and I'm happy to help as well. So as Matthias, so maybe some of you might have noticed that the original title of the talk was magnetoholography in QCD. So I was planning to talk about magnetic fields and their effects on strongly correlated systems and how to describe them using holography, and especially in the quark-gluon plasma. And this is an area of research that I feel really comfortable with, and I've been working on that for the last 5 years or so. And but then there was the suggestion from Matthias that why don't you talk about your last work, which sounded interesting. So I just took up the challenge, and well, this is the first time I'm going to give this talk. This is based on a very recent paper. Well, not very recent, but okay. So it's a paper this year in April, together with my PhD student Domingo Gallegos, who's an excellent student, by the way, and who is going to be applying for postdocs and or visiting positions next year. So just please note down his name in case you're interested in an excellent student. And this is a work on a completely different subject, and this is in fact our entrance to this subject. So this is the first time that we are studying holography and how to and in the presence of a spin current, and there are many unanswered questions. So please ask me as much as you can, and that will help us. So this is essentially just the first baby step towards constructing the holography and hydrodynamics in the presence of a spin current in relativistic systems. Okay, so so let me start. So the main motivation, essentially, so what I will be talking about is a transport of spin degrees of freedom in a strongly interacting system. Okay, so this is this forms the basis of this research field called spintronics, as most of you know. And spintronics is essentially described. It's based on transport of spin degrees of freedom rather than charge degrees of freedom, and it's extremely important in technological applications, because when you can compute, if you can construct a computer based on transport of spin flow rather than charge flow, then it just doesn't heat up. So that saves a lot of power, and that is essentially this is most of the time people are thinking about that as the future of electronics. Okay, so that's going to be spintronics. So this is extremely interesting, but of course it comes with there are a lot of theoretical problems in producing spin currents and transporting them from one point in space-time to another point in space-time, and to make them stable, and then constructing so the transistors based on spin transport, spin degrees of freedom. All of that are extremely interesting questions, and with potential technological applications. But the theory behind it is still not completely constructed, well understood. And well, there was a very recent development in this field. Okay, I'm not an expert, obviously, in spintronics, but I read papers. And so there was this recent development that is that started a new field, a new subfield within spintronics called the liquid spintronics. So this is I will talk about this experiment that started this field in the next slide. So that essentially showed a way to construct spin currents, and not only in spintronics and transport of spin in these for technological applications, but also just in other materials like graphene or Dirac and Weil semimetals, which can also be thought as strongly correlated systems. the spin degrees of freedom is playing an important role. And so what I will also be talking about is torsion. And torsion, the notion of torsion and how to realize torsion in these condensed matter systems is also is a very important thing. So these are my motivations. But these are just low energy motivations, so most of the time condensed matter systems. But in quark-gluon plasma as well, spin degrees of freedom is very important. So most of the time we don't really talk about the spins of the gluons or the fermions that are just just floating around in the quark-gluon plasma. But when they can produce certain global transports, then they are important, and that will affect the dynamics of the quark-gluon plasma. And this is something that has been also very recently, last year, observed as a polarization of a certain particle, lambda hyperon, and that is essentially just production of, if you like, spin density in quark-gluon plasma. So both in high energy physics and low energy physics, understanding spin transport is a major problem. Okay, so so as I mentioned already, I will be talking about, first, I want to start by just introducing these two experiments, one in low energy and the other is in high energy in quark-gluon plasma. So this is the low energy experiment, which started this field liquid spintronics. So you see here two different pictures, one on the left and one on the right. So the picture on the left is essentially, so this is an experiment in 2016, 4 years ago by Takahashi et al. What they did is they showed that in the presence of vorticity in a fluid, when in a liquid metal, that can be, for example, mercury or the gallium, indium, sanium, some alloy like that, when it is in a liquid state, this metal, and you can produce vorticity, and when the fluid is flowing in the presence of vorticity, you can generate some spin voltage across the pipe. And this is completely in analogy with what you would normally, how you would normally generate electric voltage in the presence of a magnetic field. So that's just Lorentz force. And here, instead of a Lorentz force, you are using a certain spin orbit coupling. Okay, so instead of the Lorentz force, which couples the vorticity to the spins of the particles. And on the right-hand side, this is some in more detail how the experiment works. So there's some friction on the boundary of the pipe. That's why the velocity is flowing with a smaller vector here. And then towards the middle of the pipe, the velocity vector is, the gradient is positive. So, and then it becomes negative. So in the middle, it flows much faster than on the boundary. And because it flows much faster on the compared to the boundary, you have a vorticity generated. So the vorticity is proportional, or it is given by the curl of the velocity field. And those are just small vortices that are generated. And because of the spin orbit coupling, these vortices are aligning the spins in the field in the liquid metal with the vorticity. Okay, so here what you see is that this is some spin density is generated that is proportional to the vorticity, and also a spin current is generated across the pipe that is proportional to the gradient of the vorticity.
Of which for questions, right? And,
hi, Jan.
I have a question. This is, I guess, basically the same thing as the spin Hall effect.
Okay.
Yeah, I don't know, right? So the spin Hall effect, very simple. How is it?
I mean, spin Hall effect is not using vorticity, as far as I know, right?
Oh, yeah, it does, in a way, I guess, yeah.
It is similar, but it's not completely that.
No, I think you're right, ain't it? So the spin Hall effect basically saying, I would just try to reconstruct in my head quickly, I sort of witness the invention of it, and right. So you're basically, how is it? Oh yeah. You have a flow of electrons from left to right. They have electric fields because you have broken parity. Yeah, that's the thing. And then because spin orbit coupling, you get an effective, in the rest frame of the electrons that works like
you get an effective magnetic field.
Spinning part spins. Now in the rest frame, you have vorticity in a way, right? So
this is really different. This happens so that would happen, for example, I mean, this happens in a liquid metal. That's why like in the presence
all clear, right? But it works by analogy, and the analogy is actually, I think, kind of close when you think about it.
Yeah, and I think well, you would know much better than me how this experiment affected the community, condensed matter community. But as far as I read from and heard from other people, that this was a big thing, right? So that
I don't think so. It's not very practical in chips.
Okay,
The end is very practical, all of it. It is not fundamental physics. It's a no-brainer.
Okay.
Can I ask a question? It seems that here in this picture, the current is along the gradient of the vorticity, right? Which is like chemical potential.
Right.
It's parallel. Whereas in the Hall effect, you would expect the current to be orthogonal to the gradients, right?
The analogy is with spin Hall and not with Hall, Carl.
That I understand that.
Yeah. Yeah,
but Hall would be non-dissipative, right? Hall would be the actual motion is orthogonal to the force.
Yeah.
Here, the driving force and the response are parallel.
That's right.
Yeah, you dissipate because you have a laminar flow, right? That is the bad news here.
Yeah.
It's not non-dissipative because the fluid is dissipating.
Yeah, there should be some dissipation which goes like square of the gradient or something. Like
yeah, just the usual laminar flow thing, right? It's a dissipative flow.
Yeah, I guess, yeah, indeed. So in that case, there's dissipation here, here too. But yeah.
And the spin Hall effect is really dissipationless. You have your point again.
Right.
Yeah. Hall effect would be dissipationless.
Spin Hall effect.
This is.
Don't think Hall.
Well, I'm a high energy physicist. All Hall physics is morally speaking.
For us, it's
but spin Hall effect is really different from Hall effect. It is like all the goodies on board.
Anyway, yeah. So let's continue. This is only motivation for me, this experiment, but I think it's this is a very interesting realization of spin current and spin voltage across a pipe that contains flowing liquid metal. And so this is an experiment. This is an example from low energy physics where the spin transport is playing an important role. There was a more recent experiment at STAR that concerns the quark-Coulomb plasma. So at Brookhaven, so relativistic heavy ion collision in Brookhaven. So the STAR collaboration, what they did is they considered off-central collisions. So here on the top left, you see a sketch of the experiment. So in an off-central collision, because of the because they are not central, essentially you have some non-trivial angular momentum to start with. The initial state contains some angular momentum that is carried by these beams that are colliding, and some part of this angular momentum goes into the quark-Coulomb plasma because that is the participants. So here you can see easier the participants that are creating the quark-Coulomb plasma, and the spectators are just flying away. So they take some part of the angular momentum away, but some remains here inside the quark-Coulomb plasma. And here you can see that in this particular setup, the angular momentum of the quark-Coulomb plasma is in this direction. So this angular momentum can be realized in different ways, depending on the parameters of the transport parameters of the system. Vortices would be generated, and there will be some total global angular momentum. So what these guys did is that they measured in these off-central collisions, they measured the polarization of a certain particle that is produced at the freeze-out when the plasma expands. So this particle is called the lambda hyperon, and lambda hyperon is here. It's just denoted by lambda, and there's an anti-particle. So this is a positively charged particle. There's an anti-particle as well, lambda bar. And what they found is that there is a non-trivial, non-vanishing global polarization. Okay, so here in this picture, what you see is that these red dots are lambda bars, the anti-hyperons, and these blue dots are the hyperons. There's a difference between them, essentially, of the polarization, because there's also a magnetic field in the system. But the point of this experiment was that both of them are non-zero. And the fact that they are both non-zero is essentially because they argue in this paper, is because of spin-orbit coupling. So there is some, the angular momentum of the particle, of the quark-Coulomb plasma is in some way translated into the angular momentum of the produced hyperons, and these hyperons are so the spin-orbit coupling aligns their spins with the global angular momentum. So they see some global polarization, and from this essentially they inferred the value of the vorticity in the fluid in the quark-Coulomb plasma, and of course, as usual with the quark-Coulomb plasma, they found a crazy number. So 10 to 22 1 over second inverse second. So that is the largest vorticity that is produced in nature. And this is an effect that was essentially, so just to give the credit to all the people involved. So there was a paper 3 years ago by Francesco, by Catini et al. And so they essentially were describing more or less the same phenomena. They were, they predicted this global higher polarization of the hyperon particle. And why, you can ask, why hyperon, why not other particles? And essentially that is because the hyperon has a very interesting property that its most common decay channel is into a proton and a pion, and this proton, so the momentum of the polarization of the proton and the parent lambda particle hyperon is essentially more or less aligned. So it's you can see here for the cross section is maximum when this angle theta star is 0. So that's why they looked at hyperons. Okay, but this shows that there is some vorticity, non-trivial vorticity in the quark-gluon plasma. And of course, you can ask all these kind of questions that if we are talking about transport of energy, momentum, and spin all at the same time in a relativistic setting, are we sure that we are including all the effects? Okay, so there can be that this is due to some other physics. There may be some other contributions. Of course, vorticity is going to play an important role, but are we sure that we are not missing an important part of the physics? So that is, for that, what we need to do is essentially to construct from start in a systematic way hydrodynamics with and transport with spin degrees of freedom.
Umut, can you say what you mean by polarization in this context?
So, the orientation of the spin of the hyperon particle, essentially.
Orientation, relative to
relative orientation relative to the angular momentum.
I see. Okay.
Can I have a question about what is the hyperon in the more, I don't know, fundamental particle term?
But it's a baryon. It's a baryon, like which decays to a proton and pion. So it's
so some heavy baryon.
Heavy baryon, yeah.
Okay, thank you.
Okay, and then the anti hyperon decays, of course, into an anti-proton and a pion again. Okay, so it's a +1, spin 1/2 particle, +1 charge, spin 1/2 particle. All right, so this is the quark-gluon plasma experiment, and this is a big thing now. I mean, like if you just look at these the citations to these papers that just like appeared last year, that it's growing quite fast, and people are trying to understand what's going on. But so the upshot, I mean, like from these experiments, I'm not going to talk about experiments. Obviously, I'm a theory guy, and what I want to so the experimental part is over. So what I want to, so my main point here is that we need to take into account all the possible sources of spin density and spin current if you want to do explore, if you want to understand these experiments, if you want to do the theory for them. So this is not only not the only reason for constructing in a systematic way the spin transport, the hydrodynamics with spin transport. Also, the spin flow is going to be related, as usual, for example, in the chiral transport it is. So it will be related to the transport of energy and momentum, charge flow and chi-relative flow. All of that, there will be some non-trivial transport coefficients that convert one of them to the other, and all of that will be should be explored. And as far as I know, in a strongly correlated system and in relativistic setting, this has not been done in a systematic way. And of course, it's also, in one last point is that it's very important to classify all the spin transport coefficients, again, in the relativistic setting. So I'm not promising that I will be doing all of that in this talk, not at all, actually. We just like took the first step towards this, and other people are doing that as well. So I think in some time we will have some complete story, but not yet. So so what we want to do is to construct hydrodynamics. First of all, the first thing that you would like to do is to construct hydrodynamics with spin flow. Okay, so that is essentially hydrodynamics with two basic operators. One is the energy momentum tensor operator, and the other is the spin current operator, S lambda mu nu. And mu nu is antisymmetric. So that is essentially just denoting the spin of the particle or a unit cell in the hydrodynamic flow of perpendicular to the plane. So this is the plane of where the spin is perpendicular to, and lambda is just the flow. Okay. So right. So the rest of the talk, the outline for the rest of the talk will be that I will first talk about the some ambiguities in defining the spin current in quantum field theory, and then I will start constructing the hydrodynamics with the spin current, and in the presence of torsion. I will argue that torsion is going to play an important role, and then I will come to the holographic description, because if you want to, for example, as usual, if you want to calculate transport coefficients that you cannot do by hydrodynamics, you need microscopic physics, and holography is the main role of holography. Applied holography is essentially in calculating these transport coefficients. And that can be done, and I will argue that that should be done in a first order gravity theory, unlike the Einstein's theory, because we want essentially the spin current, the spin connection and the field bind to be independent. And then I will take an example of a first order gravitational theory, which is easy enough to come up with analytic black hole solutions. That is called the Lovelock-Chern-Simons theory in 5 dimensions. I will define the charges and construct the thermodynamics first in this theory, LCS. And then we will find some new analytic black hole solutions. And they were all found by Domingo. So all the credit should go to him. And then we will discuss the resulting energy and spin flow in this theory. Obviously, this theory is going to be a toy model. There's no question. But the nice thing about this Lovelock-Chern-Simons theory is that you can find analytic black hole solutions, and as a result, the entire transport can be discussed in analytic terms. Okay. So then I will end with the discussion. Okay. So I'm going a bit slow, I think. So let me speed up. So let's start with the ambiguity in defining the spin current, and that is essentially in quantum field theory. This is a very well-known ambiguity, that what we all know is that the total angular momentum is conserved. So this is the basic object to look at in a quantum field theory. It has two different parts: the orbital angular momentum and the spin. So if you are considering a quantum field theory with a canonical field which transforms non-trivially under the Lorentz transformations like spin 1 half particles or whatever, these hyperons, then there is an S lambda mu nu part as well. But this S lambda mu nu part is ambiguous, because you can always redefine your energy momentum tensor by including the derivative of a 3-index object, phi. I'm denoting it by phi here, and that all these equations, this conservation of the energy momentum and the angular momentum, the total angular momentum will be unaffected. So these are called pseudo gauge transformations, and so this pseudo gauge transformation is affecting the spin current in this way. So there's a particular gauge where you can choose this phi to be exactly S to cancel it completely, and you can set it to 0. And this is usually what is being done if you want to go from a canonical energy momentum tensor to a gravitational energy momentum tensor. So this typically removes the entire spin current, renders the energy momentum tensor symmetric by removing the antisymmetric part completely, and makes the quantum field theory compatible with GR. And that is quite important, especially in holography, because holography is essentially just you start with the boundary theory, and then you couple it to GR, and then you make the GR dynamical to generate the to describe the RG flow in the quantum field theory in a geometric language. Right? So this is extremely essential in a holographic quantum field theory.
Umut, can I interrupt for a second? It's really related to connection with spintonics. I mean, the lie of all this spintonics business is that spin currents in solids are not conserved. I guess you're aware.
Yeah, I will come.
The claim is that the transport is spatialist, but the trouble is that you have to burn a lot of energy to make the current all the time. It's worked in the work, right? I'm very
yeah. I mean, like this, it's not going to be conserved.
Let me just pose a question. So the trouble is that at the moment you have spin orbit coupling, in no time you find out that actually, for fundamental reasons, spin currents are not conserved. I mean, it's a bit stronger than that. When you're dealing with non-abelian hydrodynamics, non-abelian charges are not conserved. Are you aware? You do QCD and you ask, is a color charge something, you know, in an...
But non-abelian charges are typically not gauge invariant.
The current, you can construct in case of variant current, that's not the issue.
Okay.
The issue is, I mean, I can actually send you a reference that is basically quoting a paper by the great Roman Yakif, who was worrying about it years ago. I know this reference when I entered Stanford. So all this spintronics came at the point from Stanford, from Suchen Zhang, and he put his paper in my hands, right? And
this paper by Nair,
and it's all explained why non-abelian currents cannot be conserved.
Okay.
Now, yeah, when you have electrons in solids, they feel actually the electric fields as fixed frame non-abelian fields, and therefore spin orbit coupling is working spin current conservation. But I sent you that paper.
Mm-hmm. Yeah, please.
I think you get it right because you talk about the total angular momentum, and there I agree. I didn't conserve conductive, but there's
no, yeah. I mean, like, so for me, yeah, I definitely agree, and there are different descriptions of spin transport. I mean,
no, this is unambiguous. There are lies. There are lies, and a few people are not aware of it, but they usually don't advertise it. It is the lie of spintronics. I mean, that stuff is just disappearing in no time. You have to make it all the time because you have a lot of energy.
Okay.
I sent you this reference. You know, I don't want to hold you up.
Yeah, that would be great. Yeah, I'm happy to. Yeah, let's discuss. We can also discuss that like privately. Okay. Yeah. So essentially, what I mean, like here, my main concern is that there are these gauge transformations. So what is the spin current? How do I define the spin current? If I can make this transformation. So this transformation doesn't really affect the total angular momentum, but of course it changes the spin part of the total angular momentum. So that is ambiguous. But I will fix this ambiguity by including torsion. So So to understand what's going on with this ambiguity, so in a more familiar language, if you like, let's consider a quantum some effective field theory in the presence of torsion. So let's consider, for example, a quantum field in a non-trivial Lorentz representation with some non-trivial spin, and define the effective action by just integrating out the canonical field, and then you can define the energy momentum and the spin current tree forms by taking variations with respect to the field bind and the spin connection, which are here treated as sources. Okay, so to start with, they're independent sources. Okay, so the field bind and the spin current, and from this spin from these tree forms, the energy momentum tree form and the spin current tree form, you can construct the spin current itself and the energy momentum tensor by just the usual way, by just using the field binds. Okay. At least this is not ambiguous. But then essentially this particular combination is arising. You can easily see where this combination is arising, where phi is given by S in this language, is because if you demand, the moment that you demand that the torsion, which is essentially the covariant derivative of the field bind with the spin connection as the gauge field, at the moment that you demand that this vanishes in a quantum field theory, this is typically what we do, then essentially the variations of the field bind and the variation of the spin connection becomes connected. So the energy momentum tensor that you define by varying the effective action with respect to the field bind picks up a term that is given by this term where phi is given by S. Okay, so this is the combination. That combination appears essentially because we demand absence of torsion. But torsion can be present in quantum field theories as well. In continuum description of lattices also, torsion can be present. And what I will be doing in this talk is that just to be on the safe side, I will be assuming that there is some non-trivial torsion in the system without really giving the details of how this can be realized in a particular material. I have no idea, but I'm just assuming that there is some non-trivial torsion, and I will be treating it as a source. And then, from this assumption on, I will move on and just construct the hydrodynamics. So the upshot is that the spin current is unambiguous when it is sourced by torsion. Okay, so what is torsion in a condensed matter system? Okay, so in a condensed matter system, this is something that that Jan also studied, and I'm sure he has many things to say, more than what I will be saying here.
I was just curious that you would cite it, and you did. Fine.
Sorry?
I was curious whether you would have dig this out, and you did. Thank you for citing us.
Well, yeah. I mean, of course, this is
very well.
Well, anyway, I mean, I don't want to compare all these papers, but I liked your paper really a lot, because essentially you were using a non-abelian, sorry, not a non-abelian, but a gauge invariant description in terms of Polyakov loops and Wilson loops, Wilson lines. So that is a beautiful way to do it, I think.
I had a good student and a good postdoc.
Yeah. Okay. So that is something that I like. But okay, so for this slide, the only thing that I want to say is that torsion is becoming more and more heard and becoming more important in the context of graphene, for example, because it is describing precisely the dislocations and this in this atomic structure of condensed matter systems. So, for example, you see here that this is the famous honeycomb lattice of the graphene, and there are these dislocations. So when you just close a loop, typically you close a loop by just going around these 6 atoms, and here you don't essentially close the loop. So you come up with a non-trivial Burgers vector. Here it is it's in the opposite direction, this Burgers vector. So there are 2 different types of examples of dislocations in graphene. But the basic idea is that let's assume that our underlying lattice is a square lattice given by 2 basis vectors m and n, and if you just parallel transport one of them by the other one and take the difference of the 2, that will be proportional to the difference of the affine connections with this indices exchange, and this is precisely the definition of the torsion. So torsion is going to describe precisely this what is called unholonomy. Right? So if you go around the loop, you make a loop, and then you don't come up you don't come up to the same point, but there's some non-trivial translation that you should make to close the loop, and that is given by this Burgers vector B. Okay, so this is and then in the continuum description, assuming that in the continuum limit, these dislocations are still present and described by some kind of a field that will be like a Burgers vector field. That would be different directions and different orientations at every point in space-time. Then what we need to do in this situation is to construct a theory, a continuum theory with this new field, Burgers field. All right, so let me go back to this effective field theory description, and let me first derive the hydrodynamic equation. So this is something that is well understood in the last 10 years in the presence of charge, magnetic fields, etc. How to construct hydrodynamics from effective field theory using the action language, the effective action language. And what you do is you demand the basic symmetries are intact, right? So the basic symmetries would be so in our particular case, the effective action is a function of the field bind and the spin connection. And we have to require that this effective action is invariant under diffeomorphisms and local Lorentz transformations. So and this means essentially that the sources are invariant under diffeomorphisms and the local Lorentz transformations, assuming, of course, that the path integral doesn't violate these 2. Okay, so I'm just making an assumption here. There's no anomaly in these symmetries. In that case, this will be completely equivalent to the invariance of the sources. So the diffeomorphisms is just given by this equation, so that you demand that the Lie derivative of the field bind and the spin connection vanishes, and then the local Lorentz transformations is just a Lorentz transformation, it's a non-abelian transformation where the spin connection transforms non-trivially, and so that you require this and you get other equations. So essentially, if you do these 2, what you do is you derive the word identities, and the corresponding word identities, if you do this operation, if you demand that the symmetry are the 2. The one that comes from the diffeomorphism is exactly what you would expect from you know, the Navier-Stokes equation in the absence of so in the absence of the spin current, this would be exactly that. So just and in a flat space, that would be that. So this lambda is in a curved space that is described by this field bind in general, which I'm not going to fluctuate. I mean, I'm not going to take a dynamical, but still it can be a non-trivial background. And but what you see is that, you know, this is a generalization of the conservation of the energy momentum tensor. And on the right hand side, what you see here is just a work term. It's precisely analogous to the electromagnetic work, J times E, where S, the spin current, is played the role of playing the role of J, the charge current, and R is playing the role of the field strength that is associated with the corresponding source, which is the spin connection. Okay, so R is essentially the field strength of the spin connection that sources the spin current. This is exactly of the same form. And if you demand local Lorentz transformations, what you get is, as Jan was saying, that, you know, there's a spin current conservation equation which is not totally conserved in this part, in this general case, if you have if you have a non-trivial antisymmetric part of the energy momentum tensor. But I should say that this is not the only term that would violate it, because on the right, on here, for example, if you expand, there's a connection, there's a non-trivial connection term here too. So unless you go to a completely a flat space without torsion, that wouldn't really imply that the spin current is conserved. So this is a word identity. So for me, conservation or not, they are completely equivalent to the word identities that you can derive from your underlying effective action.
So, sorry. Can you go back? I didn't understand your last comment. If I go to flat space without torsion,
so in the connection, right? So here there's this is a covariant derivative. So in the covariant derivative, there's a connection.
But and the connection,
yeah, there is an affine. There's a connection, and the affine connection has two different parts. There's the typical part that you, in the absence of torsion, right, which can be written completely in terms of the field bind, the derivatives of the field bind, and then there's a new part that is the torsion. So in the presence of torsion and in the presence of a non-trivial background, field bind background, this equation is not just D of S. This is all I'm saying.
Right, but if I go to flat space, if I set the torsion to 0, I just go to flat space.
Absolutely.
Then it's a conserved.
Absolutely.
Right.
In the absence of an antisymmetric part of the energy moment.
Well, but that will also be 0 if you don't have torsion.
Yes, exactly.
Okay. I just set the mind. So what you're just saying, Amos, is the only condition under which spin current is by itself conserved. Is that correct? Or can you figure out other conditions, other spaces where right-hand side would vanish?
I mean, yeah, so all I'm saying is that in this particular description, this continuum description, that if you demand that the torsion is 0, the space is flat, and
can you curve it somehow, or is any curvature detrimental for plain vanilla conservation?
Well, you can curve it, but then you would get a mass term essentially.
Yeah. I have no intuitions, right? I know how it works for internal non-abelian field, but here it's a bit more tricky.
Yeah.
Interesting. Okay, continue.
Yeah. Okay, so the upshot is that there's some electromagnetic force, but I will be assuming that there's a flat. I mean, I will be considering flat backgrounds from now on. So this right-hand side of the energy momentum tensor will vanish. So the energy momentum tensor will be conserved, and the spin connection may or may not be conserved depending on the whether the energy momentum tensor is symmetric or contains some antisymmetric parts.
So what do you mean by a flat background?
Yeah, exactly. Very good question. So by metric flatness.
Just the metric. So the spin connection can still be arbitrary.
Exactly, and that's very important for me to be arbitrary. Yeah.
Okay.
Yeah. Thanks for this. Yeah.
So
this is what I mean by the
Sorry.
So this is what
can I still make a question to the previous?
Sure.
Because can you go back? So because of these two equations, you know, the right-hand sides, I think they are, to me, they look very different, right? For the conservation of the energy momentum tensor, you have this usual work term, which depends on the presence of an external source, right? An external field, the curvature. Whereas the spin connection, you know, it's not an external source which appears there, it's another operator.
No, here, yes,
right?
Definitely.
And so my question, we know, for example, that the symmetric part, the symmetric energy momentum tensor, you know, is an exact dimension 4 operator. In quantum field theory, it's guaranteed that it stays dimension 4, blah, 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 blah. The antisymmetric part, what guarantees me that it's a light operator?
Yeah, exactly. So here, I mean, I should say that, so this is it's crucial for my description that the effective field theory is this field bind and the spin connection are external sources. They are external sources. I'm assuming I'm just coupling the field theory to these external sources. And you're definitely right that if you consider, for example, some kind of electron fluid, this spin connection is a derived operator in terms of, it's given in terms of these you know, the fermion fields. But that would be a completely different case, which I don't know how to describe in hydrodynamics, essentially. There the situation is similar to, say, the dynamical generation of the chiral anomaly, right? So that is hard. That's like QCD anomaly compared to electromagnetic anomaly.
It can kind of relate it, right? So to the best of my understanding, the dogma is that in our universe, you can basically forget about torsion because so tremendously weak when it would be there that we wouldn't see it. But you can have a back reaction, right? When you have spin currents in your matter, it can back react and cause torsion in the geometry. And I once saw a story that it could have happened shortly after the Big Bang because you need extremely dense matter in order to have noticeable back reaction effect. I guess you ignore back reaction effects here. You say it's all external, right? The torsion is something.
Yeah, I mean, like treating it as an external field, external source.
I think it's a very safe thing to assume, but just to be sure, right?
Yeah, exactly. But okay, I mean, but the next stage, okay, fine. So this is a starting point. So then next thing would be essentially, so just like, I mean, most of this thing that I'm talking about is really analogous to hydrodynamics in the presence of charge. So there you can also consider, for example, a gauge field, right? So this is what we all do, right? So there's a gauge field that can be treated as a source, but then you can make this gauge field a dynamical. So you can just promote it to a dynamical field. And then you can construct hydrodynamics, magnetohydrodynamics, where the magnetic and electric fields are dynamical variables as well. But this is the right starting point, I think. So from there, I think, I don't know if you can include the next step. I don't know how easy it is, how hard it is. I have no idea, but that will be essentially just to include the back reaction, yes.
But surely in heavy ion collisions, there's no torsion.
Well, I don't know.
What do you mean? I mean, it's you need gravitational torsion in a gravitational sense.
Well, the only thing I need is that when I have a fluid and I start from one point and then I go back to the same point and I just don't end up with the same point.
Yeah, but that just means your geometry intrinsically has torsion, right?
The density of the fluid, if it changes, that can also be effectively described, I think, as some kind of dislocations. Well, I don't know. I will discuss this at the end. Okay, so let me so if you like, you can listen to the talk as you know, just by considering, you know, this particular example. And in quark-gluon plasma, it's a very interesting question if there's torsion or not.
But okay, so let me ask you: do you really need the torsion, or do you just because why? I mean,
no. But I mean, look. So in these experiments, there's nobody's assuming that there's torsion. So there's non-trivial spin current generated essentially by vorticity. But for me in hydrodynamics, vorticity is a first order quantity.
Yeah.
What I want to first establish the zeroth order quantities that are the sources. Yes. And then, you know, we can set the sources to zero if you like.
Yeah, that's what I want.
Yeah.
Okay. Thank you.
All right. So so let's consider what these torsion sources can be. So from now on, well, I have just like 10 minutes essentially, but anyway, so let's move on. Let's see how it goes. So I will be assuming flat metric. So the EA is replaced by, so in this equation for the torsion, dE, the exterior derivative of the field bind, it vanishes. Field bind is flat. It's given by the delta, and it is it's here. So the torsion and the spin connection becomes the same thing essentially. So classifying torsion is the same thing as classifying the spin sources. So the first thing that we can do, we can ask is how can we classify these sources? And this is much easier to answer. I mean, this is really not a non-trivial question at all, but I think if you have never done this before, I think it's a good idea to start with in 3 Euclidean dimensions first, and then go to 4 dimensions. So in 3 dimensions, what we are talking about is a spin connection with these indices AB of the tangent space and a space index I that is running from 1 to 3. And so this AB essentially is defining the loop, the plane of the loop that we are trying to close. And this index I is denoting the direction of the Burgers vector in this case. So this is a 6. So this is a 3 degrees of freedom. This is an antisymmetric 2 tensor in 3 dimensions, and this is a vector. So there are in total 9 degrees of freedom, and those 9 degrees of freedom can be understood as essentially considering 3 different planes in 3 dimensions. And in each different plane, there may be some Burgers vector that is on the plane. This is called an H dislocation, and it has a length and it has an orientation. So that in total there are 6 degrees of freedom. And there's also the other kind of dislocation that you can talk about, which is called the Scribe dislocation, and that has only 3 degrees of freedom, where the Burgers vector is perpendicular to the plane of the loop that you are closing. So in that case, the angle of the vector is not a degree of freedom; it's fixed. The length is a degree of freedom. So there are 3 different planes. There are 3 different degrees of freedom. So this is the total 9. And in 4 dimensions, it's just it's a trivial generalization of this, if you like, but it is not so trivial because now you're including time. So it's really, if you think about it, what can be dislocations in time, it's not easy to understand. The way I understand is, well, let me come to that in the end because I don't have that much time. But essentially, just you can always consider this as in a Euclidean setting first, and then you can analytically you can bicrotate to real time, and in that case it becomes clear. So this Burgers vector acquires also a 0 component. So there is a time component. It becomes a 4-dimensional object, and here this AB is essentially so it can be on 4 different planes. Sorry, 6 different planes, and that becomes essentially 6 times 4. There is a 24 degrees number of degrees of freedom, and there is the analogous H dislocations and Scribe dislocations when this AB is spatial indices. So that I would call Wilson H dislocations. There are 6 of them, and there's the Wilson Scribe dislocations. But similarly, there is also the Polyakov H dislocations where one of these indices A or B is 0. This is also just antisymmetric. So there will be Polyakov H dislocations and Polyakov Scribe dislocations as well. Okay, so this can be described in terms of these Wilson lines or Polyakov lines distortion. But this kind of decomposition is nice in terms of understanding the physics, but it's not Lorentz-invariant decomposition because you can always make a boost to transform a Wilson line to a Polyakov line or vice versa, or just a combination of them. So that would not be a Lorentz-invariant decomposition. So what we need essentially, if you want to work out hydrodynamics, you need a Lorentz-invariant decomposition, and this can be done. So this can be done essentially by just starting with the source and separating it in terms of in the components.
Pure clarification, right? So, of course, you cannot make this product of loop things in real solids, right? Because you cannot break time translations. That's a time crystal.
That's right. Yeah, not in solids.
I think what you're just doing is using it as a metaphor, right? So the gravitational torsion can be metaphorically precisely looked at as H and screw dislocations, and when you give them a gravitational origin, you're just safe.
Right, but if you want to describe, okay, yes, but
that is not the case. I mean, I'm myself struggling a bit with
no, yeah. But what I have in mind really is that so in torsion, if you this is torsion in 4 dimensions, so it has 24 degrees of freedom.
You're safe, right? You basically have GR Einstein-Cartan theory, and there you have torsion.
Exactly, this is an Einstein-Cartan theory. Yeah, indeed, yeah, definitely. Yeah, in that case, yes, exactly. And then in quantum field theory, well, in the solids, of course, that is the dynamical torsion. What does that mean? The time direction? It's not
No,
clear.
it doesn't exist. It doesn't exist.
Doesn't exist. But in quantum field theory in general, I think it's an intriguing question to think about torsion in the fourth dimension, and that I will come to in the end. I mean, I hope that I will have time.
I think it's Eisenkarten. You know, it's straight shooting.
You can for the moment think of
Eisenkarten. It will fail.
Yeah.
Right? It's impossible.
Okay, so let's. I will try to make a wild speculation in the end that you are free to shoot. Okay, so you can for the moment think of Einstein-Cartan theory indeed. So let me just. I mean, I want to of course make my point of doing the holography in the setting. So I will just go quickly over the next 3-4 slides. And so here the point of this slide is essentially just that you can decompose in a Lorentz covariant manner. You can decompose the sources into a vector that is defined here, this B tilde, and an axial vector that is defined here, and the rest, which will be a tensor. So this decomposition is 4 + 4 + 16. And now what we have done with Domingo first was to assume that we are doing this in the presence of a flow of a relativistic fluid that is defined by the presence of a fluid 4 velocity u mu, and that this decomposition can be further decomposed by essentially, for example, taking B tilde and making it like a chemical potential term, u dot B tilde, and the rest, which would be transverse. Okay, so if you do this, what you see is that this 24 degrees of freedom is separated into one scalar, which is just mu v here, this chemical potential, and there is an axial chemical potential, a pseudoscalar, 2 transverse vectors, transverse to u mu, 2 axial transverse vectors that are coming from this, and also 2 from the one axial, one vector from the tensor part. And what I mean by axial here is just, it's antisymmetric under parity transformation. Right? And then there are two traceless transverse symmetric tensors with 5 degrees of freedom. So in total, there's 5 + 5 + 4 × 3 + 2, which is 24.
Umut, I probably missed something. I thought the torsion was external.
It is.
So what do you mean in this equation that you wrote? If u mu is external too?
U mu is not external. No. But this is just no. Yeah, exactly. So this is essentially just decomposing omega by using this u mu. That's the only way that you define it. So you can define.
Oh, you're defining mu a. I see. Okay.
Exactly. Yeah. I'm defining mu a. So mu a can be defined, for example, by multiplying with the appropriate.
Yeah. Okay.
Right. Yeah.
Thank you.
So you can, it's quote unquote constitutive relations would be as follows. So first of all, in the most general setting, we should allow for an antisymmetric part of the energy momentum tensor. So the energy momentum tensor would have an energy part, the pressure part, and then in general, these are of course frame dependent objects, but in general, you would have energy currents, and there is a Q bar and Q that are in general, they will be different because I am allowing again and for an antisymmetric part of the energy momentum tensor, and that will be a symmetric part, which typically in the absence of any non-trivial sources like magnetic fields or torsion in this case would just vanish, and that would only pick up a non-trivial contribution at the first order level. That would be like the shear viscosity, or bulk viscosity. But here there can be some order 0 contribution that is essentially determined by the sources, and then there is the antisymmetric part as a antisymmetric two tensor, which is called an intrinsic torque. So this is the most general decomposition, and then the spin current can also be decomposed completely analogous to this to the decomposition of the source of the spin current. And instead of just going through this equation, what I will do is I will just show here a table. So these are the spin sources, these are the spin currents, and these are the number of degrees of freedom. Okay, so I will, whenever we see an equation, I can come back to this table and show what I mean. Okay, so
so hold on, sorry. what are the dynamical degrees of freedom?
The dynamical degrees of freedom would be just 6, right? So that would be, for example, this N, A, and V. Because what you need, like if you do the, so can I come back to that at the end?
Sure, yes, sure.
Yeah, because I have like 3 minutes and.
Sorry, yes.
No, but that's perfect that you're asking all these questions. So let me give a try to give a short answer.
Sorry, Umut, I'm taking over as host because Matthias disappeared. Of course, you have more than 3 minutes because there's been a lot of questions. So you have at least 15 minutes. I mean.
Oh, okay. Well, thanks, Daniel. I mean, of course, like, so this is the nice thing about the webinars, right? People can just disappear at will.
I was trying to say that.
Like, you know, they can keep their name there also. So that would be a fantastic way of just attending all the seminars.
Just for the record, I did not disappear. I lost connection.
Okay.
Yeah, okay. That's what I meant, of course.
Okay, yeah, well. Okay, anyway, so thanks. So, but anyway, I mean, I don't want to take too much time. So, yeah, thanks for all these questions. So what I was trying to say here, well, so when I call it quote unquote constitutive relations and almost immediately quote me here is that this is not complete, right? So because what you have, for example, in the charged fluid is that you have a J mu. So you have a source A mu, which has 4 degrees of freedom, which can be decomposed into a spatial vector and a scalar. But then the spatial vector part is not an independent degree of freedom, right? That doesn't properly. So the corresponding operator that couples to that source of vector A is not independent. So the corresponding J mu is going to be given just determined completely in terms of the chemical potentials. That's just mu times U mu. So here the same thing should happen. And if you just look at the dynamical equations of motion or for the spin current, what you have is just del lambda S lambda mu nu equals something. So there are 2 antisymmetric free indices, which gives you 6 degrees of freedom. So 6 equations, and there should be corresponding 6 degrees of freedom to fix. And those would be essentially this NA and NB. Okay, and the rest would be just background. Okay, so
thank you.
I hope I understand.
Thank you.
Answer the question. That are, I mean, why NB and NA? That's because if you set this lambda to 0, those are the, and if you track through all this change of variables, you find these 2. Okay, so now the holographic description. Okay, so this is gonna become more and more uncontrolled as we go towards holography. Obviously, because I don't really know if all I've described can be so far can be described in holography in a usual second order holography in a non-trivial way. Probably it can be in supergravity. I will just come to that in the end. But so for the moment, to keep the discussion completely parallel to what I've described so far, to have an effective field theory with the field bind and a spin connection, degrees of freedom independent of each other, and as background, I want to consider first order gravity. So in first order gravity, this is built in. So what I mean by first order gravity is essentially a gravitational theory with independent field bind and independent spin connection, which are now dynamical. And that would be only non-trivial, of course, in the presence of bulk torsion as well. So the bulk torsion will become the boundary torsion as you move towards the boundary, and the bulk torsion is an important player here. And what I also want to do from this first order gravitational theory is to give me analytic solutions, because without analytic solutions, it's almost impossible. If you have seen all these, index structure, this is really hard to keep track of by just numerics. So it's really nice to have some analytic power. And for that reason, we decided to consider a particular first order gravitational theory called the Lovelock-Chern-Simons ADS gravity in 5 dimensions. That was first constructed by Shamseddin in '89, and then many people worked on it and derived the basic degrees of freedom, the canonical description, etc. And so this is just a Chern-Simons theory in 5 dimensions. So this is a gauge. So description of gravity as a gauge theory, special kind of gravity as a gauge theory, based on the ADS group algebra, SO4, 2. So G, the group algebra here. So A is a connection of this group. And well, a a couple of comments. Chern-Simons gravity is well known to be just topological in 3 dimensions, but in 5 dimensions or more, this is not the case. So in 7 dimensions, 5 dimensions, 7 dimensions, etc., it is for a non-abelian Chern-Simons group. It has non-local propagating degrees of freedom in the bulk. But also, as usual, as analogous to the 3-dimensional example, the boundary dynamics is quite rich. So as you know, like in the 3-dimensional Chern-Simons gravity, what you have the boundary theory is a cut. It gives you the asymptotic symmetries. If you just look at the asymptotic symmetries, you find the Virasoro generators. You find the Kac-Moody symmetry if you have a non-trivial group G in general. And this is analogous in 5 dimensions. What you find is a Westumino-Witten 4 conformal field theory. So this is the boundary symmetries of these theories is isomorphic to the symmetries of the Westumino-Witten 4 conformal theory, which was first introduced by Nair and Schiff in the 90s, and then many of its properties were studied from a conformal field theory point of view by Losev, Nekrasov, Moore, and Shatashvili in 95. But this is not a well understood theory, but I mean, there is some rich boundary dynamics. So this is essentially giving you some hope that there will be some non-trivial bound. So it may be dual to some non-trivial boundary theory, which may be some this theory or it's some deformation of that. Okay, so let me, okay, so I don't want to get into too much details, but let me just give you one slide. So forget about this. What I'm doing here is just I'm mapping this Chern-Simons theory to a more usual form of a first order Einstein-Cartan gravity by just essentially identifying the generators of this connection, SO4,2 connection, by the translations in 5 dimensions and the rotations in 5 dimensions. If you do this and the associated the field strength, if you just plug this in the Chern-Simons action, you get a more familiar looking action, which is a first order gravity in 5 dimensions. And there's a RHIC term, there's a negative cosmological constant term. If you look at the ADS solution, that would give negative cosmological constant, and there's an R² kind of term. And if you just expand this R² in terms of the space-time indices, what you would get is this is exactly a Gauss-Bonnet with a particular coupling, lambda Gauss-Bonnet coupling 1/4. Okay, so this is a very special theory, but it is similar to Gauss-Bonnet if you like, if you want to think in those terms. So there is a non-trivial, there's a standard ADS solution with for vanishing torsion. So you can set the torsion to 0. This is a consistent solution to this theory. But there are naive solutions, other solutions with propagating non-trivial torsion. In particular, there are black hole solutions that I will show. Okay, one last comment about this theory is that the holographic renormalization in this first order gravity has been studied by Baniados, Miskovich, and Tyson in 2006, and in particular the counter term action has been determined. So you can go ahead and calculate the free energy, you can calculate the entropy. This is one thing that we have done in our paper as by using the Boltz's idea of defining it as a charge at the horizon. This can be done in this theory given by this equation. If you calculate on shell, that will give you the entropy of the corresponding plasma. And the total mass of the black hole can also be calculated. So there will be some Komar mass kind of term, which is this one. And then there will be some term that comes from the connection that comes from the spin sources. Okay, so the associated charges, spin charges. And all of this theory, so all the black hole solutions that we are looking at would satisfy. Essentially, because of these definitions, you can immediately show by straightforward calculation that the free energy that you define from the on-shell action is going to satisfy the Samar relation, just the energy minus Ts minus mu times Q, where Q is the spin charge. Let me repeat: spin density and the associated chemical potentials, and the first law. Okay. So let me. So the nice thing about this first order gravity is that you can solve equations of motion by using algebraic tricks. I'm not going to get into details. I have some backup slide. If you're interested, we can discuss later on. But let me just go directly into the results because there's not much time left. So if you go there, what we have found is that if demanding regularity at the horizon, you have two different kind of solutions, two different class of solutions. One class of solution has a single spin source, which is given by this A2, what I defined here. as this vector A2 here, this one. And all the other sources are set to 0. And the first thing that you see is that you can work out the thermodynamics by using these equations. And what you find is that this is a conformal fluid. Okay, so this P is exactly minus 1/3 of the energy. And there is a non-trivial shear part, the 0th order contribution to the shear tensor of the energy momentum, so the symmetric traceless part of the energy momentum tensor. And at the first order, of course, there would be, you would expect some shear viscosity term, etc. But here, at 0th order, there's already a non-trivial contribution that is coming from these sources, the spin sources. And the spin current can be calculated analytically as well. And this is the result. Okay, so you have essentially a non-trivial spin current. And one important comment that I want to make is that you can make, so this theory, so there is no antisymmetric part of the energy momentum tensor. So remember, the energy momentum tensor is just given by this. So you would only have an antisymmetric part if you have Q and Q bar different than each other. In this particular example, they're both 0. And or if you had the T mu nu, which is non-trivial, but in this case, it is also vanishing. So there is a non-trivial, so the energy momentum tensor is symmetric. And so there is a conserved spin current, even though it's not sourced by an antisymmetric part of the spin current. It is entirely sourced by this source that corresponds to this torsion, this particular type of torsion. Okay. And the coefficient of this transport coefficient is completely determined in terms of t square, and this is something that you would expect in a conformal theory. But the coefficient is, this kappa is just the coupling in front of the action. Okay.
What breaks parity?
Yeah, that's a very good question. What breaks parity is that the source breaks parity, right? So this A.
I mean, the existence of the epsilon tensor.
It's because so if you would only get a non-trivial spin current in the presence of this this vector source, which is an axial vector, only if you include the epsilon tensor. Yeah, exactly.
So the source is axial. Okay, thank you.
Yeah, the source.
A very quick question, Umut. Right, so your source is torsion, right? Your A2 is basically injection torsion in the system, right? And
a component of
the relationship between torsion and shear, and I guess there is the origin of this pi mu nu. It's basically like a shear, right? A shear pressure, how to call it.
Yes. Sorry.
So when you shear a solid, the dislocations start to run. They feel a force. And
right. Yeah. But are we? Is it? But what you mean by shear, I think in that case is when you include a derivative of the sources. So that would be like a shear in the usual sense where it's proportional to the derivative of the fluid velocity. So that would be like a shear.
I mean, a shear force has the same status as a pressure, right? The same thing when you externally apply it.
Okay. So this would be
a shear force. And then the dislocations start to accelerate. That's metal working.
Okay.
Right, and geometrically, a dislocation, as you explained, is torsion. So I think it's a rather natural relation, if you ask my opinion.
Okay.
Talk about it.
Okay. Yeah. Okay. Yeah. Great. Yeah. So good to, I think good to have this interpretation. Yeah. Thanks. Okay. Another type of solution, as I mentioned, is that there is a different class of solutions which has it's much more complicated. It has the three of these sources turned on. There's a vector, and there's an axial scalar. There's a pseudoscalar. There's a vector, and there's a tensor C. So here, this is the thermodynamics again. So you can work out the thermodynamic charges directly from those equations that I showed 2 slides ago. And what you find is this is also a conformal fluid. So, I mean, this is what you would expect anyway. So the Lovelock-Chern-Simons gravity is always going to give you some conformal fluids. But the nice thing is that this conformality is not really broken by these sources, and that's also something that you expect. And then this is a different example. I mean, the reason that I'm showing this example here is that because this has some non-trivial antisymmetric part of the energy momentum tensor. So for example, Q bar, the energy current Q bar, and the other energy current Q are not the same. So this gives you an antisymmetric part, and there's a non-trivial intrinsic source in this case as well. And again, here you can construct a spin current and a couple of comments. So this is a conformal fluid with different spin sources, so it's more complicated. But again, you have a non-trivial spin current even in the if you have a symmetric stress tensor, because you can set this Q bar, sorry, this Q to 0, for example, by setting A1 to 0, and you can set this to 0 by setting V to 0, but still you would get a non-trivial spin current coming from this term, okay, and this term. So this happens, like you have a non-trivial spin current in this holographically renormalized theory, and you get that from this, you read off from the 1-point function, even in the absence of the antisymmetric part of the energy momentum tensor. And this is exactly what you would expect, because in this conservation law for the spin current, there is also this connection term, which is non-trivial in the presence of a torsion. Okay, so and then there's a non-vanishing intrinsic torque and energy currents. So let me now go ahead and the last thing that I want to show, don't worry, this is just one before the last slide, that you can now go ahead and once you establish the zeroth order contributions, you can go ahead and just make your black brane, the components of your black brane dependent on the space-time positions, and then expand in derivatives and use essentially, in other words, use the fluid gravity correspondence to first order, for example, to identify and calculate the transport coefficients. So this is what we have done. I mean, we haven't carried out a systematic analysis that's just, let me say, from the onset, but just to see some non-trivial spin transport, whether we can describe some non-trivial spin transport and calculate their coefficients, and it is possible. So for simplicity, what we are assuming here is that I will be describing first order solutions in the derivative expansion for this black brane in 5 dimensions, but only in 2 different sets with this axial chemical potential non-vanishing, or the vector spin source non-vanishing. So for the first class of examples, you see this, you find the vorticity. Okay, so the reason that I'm doing it essentially because to connect it from the first slide. Yes, go ahead.
Can I ask you something? Yes. But it's related with like the previous solution. So you don't have no, I don't mean this one. I mean the other one. Okay, here. So this is just like zero ordering derivative, right?
Yes.
Is that an equilibrium state?
Yes.
Are you transporting something?
Well,
I mean, you have this S lambda mu nu. Is that S lambda mu nu describing the transport of something?
Yes, but I don't think that it will generate entropy. I mean, that depends on how you describe transport, right? So there's dissipative transport, this is the dissipationless transport.
So your spin current is dissipationless, right? Just because of the tensor structure.
Because, yeah.
This is like hydrostatic equilibrium. He just doesn't have a metric. He has a torsion that's turned on.
Right. There is just in the presence of a source, you have this this response. Essentially, that's it.
But that's flat space.
In flat space, yes, in flat space. But I think your question is just right on the point that.
I mean, because it's like kind of confusing to be like in an equilibrium state in which you will have transport, actual transport.
But it is not really. What do you mean by actual transport?
I have a constant electric field. I have transport. Constant electric field. I have a beautiful constant current. It's fully equilibrium.
Yeah, in the presence of magnetic field, the same thing happens. By the way. Sorry, Conrad, did you say magnetic field?
An electric field, but it doesn't matter.
Yeah, it doesn't matter. Yeah, exactly. Yeah.
A constant source, time-independent source. you can have constant transport in an infinite system. In an infinite system.
Exactly. Yeah.
Okay.
But I think it's an important question. Well, I mean, I will come to that in the end. So so it's important to classify the different kind of transport that you have in the system by studying the entropy current. Okay, so and asking whether the particular kind of transport here generates any entropy or not, and that we haven't done. So this is, in that sense, we haven't done a systematic study of
Can't you decide it from the structure of the tensor?
Yes, well,
the usual arguments, right? That you time it first, and then you can figure out whether.
I guess so. Yeah, I guess it's not hard. I'm not saying that it's hard. Yeah, we just haven't done it.
It applies here, you know, else by opinion.
Yeah.
It's sort of stronger than electric currents. These things
Yeah,
are really specialists. They can easily systemic downstate. Also
exactly.
Yeah, sorry to jump in, but
not much time.
These are really interesting questions. But can we let Umut get to the point?
Yeah. Okay. So let me wrap it up. So let me show another picture at least. So there are a lot of equations here. Well, thanks, by the way, for all these nice questions. So so let me just skip the other example. Just consider this one, for example. What you have here is that if you just express it in terms of the spin current, the kind of transport that you get, you see exactly the type of transport that you need, which is a polarization or spin density or spin current generated by vorticity. So there are two different terms. There's an immediate response to the kind of source that you have, which is this term, which is something that you expect. But there's also, at the first order, what you get is vorticity, and vorticity also contributes to the spin current. So there is some kind of spin orbit coupling in the system. And so you can generate essentially. So this is very similar to the chiral vortical effect. So this is kind of a parity odd vector that you generate. It's not about chiral. So this is not imbalance of chirality, but it's an imbalance of chiral component of the spin. But still, it's analogous to chiral vortical effect. But here also there is an intrinsic torsion generated by this derivative of this mu a. So it's a little bit different as well. It's in some sense it's more akin to what is called very recently by this lattice gentleman, Imaki and Yamamoto, that it's a chiral torsional effect. So they studied torsion on the lattice and in 4 dimensions, and they've seen essentially more or less the same thing. But there, you can also make a different interpretation of this in terms of what is called the Barnett effect. So Barnett effect is discovered by, it's essentially a magnetization of an uncharged body by rotation. So this is something really easy to understand. In the presence of just electrons, you have some rotation, and the rotation in the presence of electric fields. Of course, if you go to the rest frame of these electrons, there would be some magnetic field which would align the spins, and so that would be just like aligning the spins by rotation. So that happens in uncharged bodies as well. This was discovered by Samuel Barnett in 1915, and well, very recently, again in last year, the nuclear version of that was observed. So here you see that rotation is generating some magnetization in the nuclear spins. And so this kind of like, I mean, what we have seen here is something really along those lines. Vorticity is just giving some magnetization, and that is also true for an uncharged body of system. And we are describing in our plasma with this conformal holographic theory. This is uncharged, so this is a more or less similar thing. So it's a dynamical version of the Barnett effect. So let me just skip. Well, yeah, let me not skip it, because there's some interesting novel transport that you can identify. For example, this one is generating some kind of vector component of the spin current proportional to del U compressibility, and there's a new term here that is proportional that looks like a vortical Hall spin current in some sense, because this V2 is the source, but the spin current that you generate is perpendicular to both the source and the vorticity. So it's a bit so there are all these different type of transport is possible to generate, and I think my upshot is that if you work out systematically all these details of the holographic theory, you can discover different kind of effects, and which is which are interesting to analyze by themselves in just directly, for example, in quantum field theory, I would say, in the presence of torsion. Okay, so let me summarize. So what I wanted to, well, the first thing that I wanted to make, the first point I wanted to make was that there is a strong demand in developing relativistic hydrodynamics with spin these days. As you have seen, many of these key references in this talk was in 2019, very recent. And I argued that torsion is acting as a source for the spin current at the zeroth order source. So this is what I want to describe in hydrodynamics. So we've derived the hydro equations for the spin current and the energy momentum tensor in the presence of torsion, and constructed constitutive relations up to identifying, of course, the dynamical variables, etc. So this is something that is left to do. And then, you know, I hope that I convince you that this Lovelock-Chern-Simons theory is a particular toy model, which is very fruitful to study spin transport. And you can, by using this, you can come up with novel spin transport properties. So, well, the work left to do is to do a systematic study of relativistic spin transport, calculate essentially deriving the entropy generation, the entropy current, demanding that it's positive definite, setting some of these spin transport coefficients to zero, thereof, studying the Onsager relations between different spin transport coefficients, etc. So all of that remains to be done, and to do some analysis at weak coupling. So this is quite interesting, I would say, because we have these precise values for the spin transport coefficients, and whether if you can get the same numbers by just doing a weak coupling quantum field theory calculation, that would be quite interesting. Because it would indicate some kind of universality in this underlying transport. So that happens as Carl established and Francisco established. That happens in chiral transport. Okay, so the same thing is like it may happen in spin transport as well. So this is an open question to me. And one very interesting thing to do is to go to more general holographic theories, and for example consider supergravity rather than some exotic gravity theory with torsion. Just consider supergravity because torsion appears naturally in supergravity. As you all know, you can get rid of torsion by including fermionic matter, and this happens of course in supergravity. So that may be interesting to study this in supergravity. And then, well, the last question is whether there are some observable effects of the novel spin transport. So let me finish here. Thank you.
Yeah, thank you very much, Umut. Thank you everyone for the questions. Daniel, could you stop the recording for me, because I don't have host privileges anymore.
Okay, no worries. Just let me point out that there was a question in the chat asking you, Umut, about the case group of the why SO4,2 and not SO4,1 in the case supergraph.
Yeah.
Sorry, the connection is...
Matthias, can you hear Matthias? No.
No, is that Matthias' connection or my connection?
No, I think it's Matthias.
Okay, yeah.
I was just pointing you to this question in the chat.
Yeah. So that's essentially that's because if you want to get a ADS solution in 5 dimensions in this Chern-Simons theory, you need SO4,2. That's the group of that's the ADS group.
Yeah.
In 5 dimensions. This is exactly that matches the conformal, the global symmetry of the corresponding conformal field theory in 4 dimensions.
Mm. Okay, thanks, Umut. Okay, there's been lots of questions, but if there is one last question,
I mean, I can show more detail if you like. So here, for example, by the way, I think for any kind of questions regarding this theory, the best reference by far is this. Well, there are really good references. So Zanelli has a review, and this is a very beautiful review in 2005, and he describes all these Chern-Simons gravities and like in a general way. And this other really nice reference is this Paniados, Miskovich, and Tyson in 2006. So here you also see where this identification is coming. So this identification is essential, this SO4,2, essentially because you identify the sixth, one of the 5 components, and the sixth, when you consider this this generator, that will be identified with the translations in 5 dimensions. So that's so you need more than SO4,1.
Right. Okay, that's answered. I don't know if there's probably any last question. No.
I'd like to ask one last question.
Go ahead.
So as far as I understand what you're saying regarding torsion, or maybe you're not saying it, but the way I want to think about it is that it allows me to derive a very particular spin current, in the same sense that when I couple my theory to a stress tensor, it gives me couple my theory to a metric, it gives me a good stress tensor. So the question is why, I mean, do you have some explanation or intuition about why the spin current that you obtain this way is the spin current that's observed in, say, RHIC or LHC?
I don't have an explanation. So, but I want to make a wild speculation, if you allow me.
Yeah.
Because, we are among friends, and sure. The recording has stopped. So, so I
can stop it if you want.
Well, no, okay. So let's see. Anyway, I don't mind.
I can stop it if you want.
I mean, I didn't want to include that in the talk, in the bulk of the talk.
Then I stop recording.